So in this example, we are told that arm ABC is, we can assume that it's a single rigid body, right? This arm going from there to there, connecting to the main structure at point A using a pin, let's say. We know the mass of that arm is 320 kilogram, and the moment of inertia about its center of mass right there is represented by this black and white colored dot circle. Its center of mass is, well, we know the mass moment of inertia about that center is 360 kilogram meter squared. We are told that point A is stationary, so the whole structure is stationary, and point A is attached to it. Right? It's a pin. It's stationary, and this arm can rotate around point A. So it's a rotation about a fixed axis, right? The axis passing through this point, which is coming out of the screen or going into the screen, depending on which direction you take it's positive. And the hydraulic piston, here is the hydraulic piston attached to this arm at point B, is exerting a 14 kilonewton force on the arm at B. So it's expanding and pushing this arm up this way, and we know how much force is exerting on this arm. That would be 14 kilonewton, and because of that force applied to the point B, we are going to have a rotation about point A for the whole arm structure. Now we are asked to find the arm's angular acceleration. Let's see how does that work. Well, I know it's a motion about point A, so rotation about a fixed axis, and that axis point A. So I can always start with summation of all moments about point A is equal to IA, mass moment of inertia about point A, times acceleration. The motion is counterclockwise, so I take counterclockwise as positive. Now, we are looking for acceleration, but the problem is we don't have mass moment of inertia about point A. We know what mass moment of inertia is about about center of gravity, center of mass of gravity, and that's 360 kilogram meter squared, but we don't know IA. So before I use this to find angular acceleration for that arm, I have to find out what IA is. So let's go. Let's go there and start from there. Well, it's a single structure. It's not something that I can decompose into other parts. I'm already given what the mass moment of inertia for the whole structure is about its center of mass. So all I need to do is just use parallel axis theorem and find out that now that I know what the mass moment of inertia about this axis is, I can find out what is the mass moment of inertia about point A as long as I know the distance between these 2 points, which are axis, again coming out of the screen, and the mass of the whole structure. As far as I know these two, I'll be fine. I can find the mass moment of inertia about point A. So let's see. Mass moment of inertia about point A is equal to mass moment of inertia about center of gravity, CG or G. I'll use both to represent mass moment of inertia about center of gravity. I use them interchangeably. They both mean the same thing. Mass moment of inertia about center of gravity or center of mass. Okay, so IG, well, this is the mass moment of inertia that I'm given. M is the mass of the structure. I know that 2 is 320 kilogram. So only thing left is I have to find out what is the distance between point A and center of gravity. So I'm looking for this distance from A to center of gravity. This is my D value. How can I find that? Well, look at this right triangle formed by this line. Right? Well, this line is the hypotenuse of this right triangle. I'm looking for this. I know what this distance is 0.8 plus 0.3, which is 1.1. I know what this distance is. It's 1.8. So in this right triangle, I know the opposite side. I know the value for this side. I can find what is the length of the hypotenuse. That would be, I can just write it here. D is equal to square root of 1.1 squared plus 1.8 squared. I'll just leave it like that. Now I'll come here. Well, I know Ig is 360 kilogram plus m, which is 320 times that square root squared. 1.1 squared plus 1.8 squared. The whole thing is a square, so I can get rid of the square root. If you do the math, you will get 1780. I don't like the way I wrote this. 1780 kilogram meter squared. That would be my mass moment of inertia around about point A. So now going back to main equation, now I know what IA is. I can find the moment about point A. I know pretty much all the dimensions, and I know the force applied by this hydraulic jack to hydraulic piston to my to this arm, so I can find out what alpha is. Let's see how can we figure that out. Well, dynamics start with free body diagram. Let me see if I can bring this image here and make it smaller. It's hard to draw, so I can use it both for kinetic and free body diagram. I don't know if it's gonna work. It's too small. I'm gonna try. So I'm gonna put it there, and then move it this way. Make a copy of it. Put it next to this and make sure it's alright. There you go. So that would be the equivalent. This is free body diagram. The left one would be my free body diagram. This is free body diagram, and this is I'm going to use for kinetic diagram. Okay, so looking at the arm, what forces do I have? I have two forces, right, from the support at A, so I'll put it here. I have A, if I take this Y, well, it is Y, this is AX, right, apply to this point A, this is point A. I have weight, so this is mg. I apply to center of gravity, or weight is applied, I put it always in the center of gravity. And I have the force vector from, let me just draw it in different colors, from this hydraulic piston. Let's call this FB, is applied to point B, like FB. It's a little crowded there. And what happens in kinetic diagram? Well, these are all the forces in kinetic diagram. Well, rotation about point A, so only thing I have is angular acceleration. That would be, let me raise that so I can put it a little higher. IA alpha, right? Mass moment of inertia about point A times angular acceleration. Now let's write the equations. One thing you have to pay attention is, well, I'm writing the equations, like I'm forming this equation about point A, obviously. So AX and AY are gone. They're not creating any moment about point A. Now I have mg, mass. Well, mg is downward. I took counterclockwise as positive. I know the distance between weight and point A, so that creates a moment in clockwise direction. So mg times 1.8 clockwise direction. So that would be negative. Let me rewrite it here, and A is equal to IA alpha. Positive is this side, direction of the motion. So I'll get minus mg times 1.8, pretty much it. Now, other force, the only force, other force that creates the moment or moments about point A would be the force applied to this arm by that hydraulic piston. Now, that force is in an angle. I have to find out what I'm going to do. Are there two possibilities? I can find what is the distance here between the perpendicular line between the line along this force and point A and multiply that by FB, or I can find the components of FB along X and Y and multiply those components, each of those components, with the distance they have with point A. So what I'm trying to say is, let me see if I can draw it here. I can erase this. We don't need that. FB, so this is FB. Right. And then we have our point A somewhere, let's say there. It's not in scale, but now I can find FBX, FBY, and then as long as I know the distance they create or they have with point A, I can find out the moments they create. So Fx, let me try to draw it in a better way. So Fx multiplied by this distance is going to create a moment in this direction, this clockwise direction, so that would be negative. And Fy, I forgot y there. Fy is going to create a moment about point A in counterclockwise direction, so that would be positive. Now, in order to find these, I need to know what this angle is, like theta. I'm going to call it theta. I need to know what this angle is. How can I find this angle? Well, this angle is it. Let's look at the main structure. Here is the angle I'm talking about. Erase that too. Here is the angle I'm talking about. This angle, right? Theta. Now, this angle would be whatever I have in front, and whatever I have in. I can find it as a tangent. So this angle is equal to this angle there. And this angle is tan inverse. I can just write theta as tan inverse. What do I have there? In this right triangle, right here, I have the summation of these two as the front part, which is 1.5, divided by the side, which is 1.4. So tan inverse of 1.5 over 1.4. Right? This is the right triangle, this is the opposite, and this is adjacent. So 1.5 over 1.4. That would be 1.5 over 1.4. That'll give me, let me see what I got there. I got theta as 47 degrees. So I can find theta. Now I have theta. Once I have theta, I can find the components of FB in X and Y direction and multiply them by the distance they have from point A. So let's do that. Let's go with the Y direction. So the plus the component in Y direction would be FB sine 47 degrees times the distance it has. Well, in Y direction, that would be the distance. That would be 1.4 times 1.4, and then minus, I'm looking at the component in X direction. As I said, it creates a moment in negative clockwise direction, which would be negative based on the assumption I made for the positive direction. So that would be FB, whatever it is, cosine 47 degrees time the distance. Well, what is the distance? Let's take a look. We have this one, so it creates so the X component would be this direction. The distance it has from point A is 0.8 and 0.8 meter. So there goes 0.8 meter, and the whole thing would be equal to IA alpha. From there you can find alpha. We know everything we want. Alpha would be FB sine 47 degrees times 1.4 minus FB cosine 47 degrees times 0.8 minus 1.8 mg. The whole thing is divided by IA. We know what IA is. We know what FB is 14 kilonewton. We know what M is 320 kilogram. Well, G is the acceleration of gravity. Plug them in, you can find alpha. So alpha becomes 0.587 rad per second squared. There goes the alpha we were looking for, the angular acceleration of this arm.